The Laplace transform turns a differential equation in T into an algebraic equation in a new variable, S. We want to solve the equation y double prime plus 4y equals 0 with the starting conditions y of 0 equals 0 and the derivative of y at 0 equals 3. Recall that the Laplace transform of y double prime is s squared times y of s minus s times y of 0 minus the derivative of y at 0, where capital Y of s stands for the Laplace transform of y of t. Applying the Laplace transform to every term in the equation gives s squared times y of s minus s times y of 0 minus the derivative of y at 0 plus 4 times y of s equals 0. Now substitute the initial conditions y of 0 equals 0 and the derivative of y at 0 equals 3 into that equation. This simplifies to s squared times y of s minus 3 plus 4 times y of s equals 0. Collecting the y of s terms together gives the quantity s squared plus 4 times y of s equals 3. Dividing both sides by s squared plus 4 gives y of s equals 3, divided by the quantity s squared plus 4. Recall from the table of transforms that the Laplace transform of sine of a t equals a divided by s squared plus a squared. Here, a squared equals 4, so a equals 2, which means our expression matches the sign pattern with a coefficient of 3/2 in front. Reading this off the table, the inverse Laplace transform gives us y of t equals 3/2 times sin of 2t. Now check the solution. Differentiate y of t equals 3/2 times sin of 2t twice with respect to t. The first derivative is 3 times cosine of 2t, and the second derivative is negative 6 times sine of 2t. Substituting these back into the original equation, negative 6 times sine of 2t plus 4 times 3/2 times sine of 2t gives negative 6 sine of 2t plus 6 sine of 2t, which equals 0, exactly as required. Finally, check the initial conditions. At t equals 0, y equals 3/2 times sine of 0, which is 0, matching y of 0 equals 0. Also at t equals 0, the derivative equals 3 times cosine of 0, which is 3, matching the derivative of y at 0 equals 3, so the solution checks out completely.